All right, here we go. Okay, so in Calculus 1, you investigated two primary problems in calculus. The first one is, you know how much of a quantity you have at every moment, and you want to know how fast the quantity is changing at every moment. There are some seats here in the middle if you make your way in. There are some seats left. Okay, the other problem was, you know how fast the quantity is changing at every moment, you want to know how much you have. So, whether you knew it or not, that's what you were doing in calculus. Maybe they didn't tell you. But this is what you were doing in Calc 1. One of these two, you're always working on one of these two things. Okay? In Calc 2, we'll touch on both, but most of Calc 2 is looking at endeavor number 2. Okay? You know how fast the quantity is changing every moment. You want to know how much of it you have. Oh, so I forgot to mention. So all of the lectures are screen recorded. We're recording right now. And so I'll post those on Canvas. That's not instead of coming to lecture. No, that's because you learn by repetition. You know, so all this stuff you're seeing for the first time, right? You walk out the door, oh, I got 90% of that. That was an awesome class, understood it. And then what? You have lunch. And you go to another class, and then you play football, and then you do your laundry, and then you have dinner, and then, you know, you hang out with friends. And now what? You've only seen it once. It's starting to fall out of your brain, right? That's what the video's for. So watch it that night, watch it the next day. It's the repetition that will solidify it and reinforce it. Okay, that's what the videos are for. Okay. So here we go. You know how fast the quantity is changing at every moment. You want to know how much you have at every moment. So what I want to do is, I want to do a crash course of that in the first week or so. We're gonna like what you spent months on in Calc 1. We're gonna do a review crash course here in Calc 2 for the first week, because really this is most of Calc 2. A lot of Calc 2 it pertains to this endeavor. So I'm going to take you through a list of principles, and so kind of as an initial principle, principle 0, variables vary. Variables vary. Okay, so when you see this, 2x minus 7, what do you think? What do you think when you see this? So how many people think x equals 3.5? Right? That's what you've been trained. You have an equation. You're trained to see this x as it's like the unknown number, right? Unveil the curtain, it's 3.5. Okay, so I want to give you a different view of that. Could x be 4 or 10 or negative 0.5? Is there any possible way it could be?
Could be, but it wouldn't be right.
Okay, he said it could be, but it wouldn't be right. Exactly. X could be 4, but it just wouldn't make that equation true, right? It'd be, well, you get 1 equals 0, and so that would mean untrue statement. Okay, so suppose that x has a meaning in the real world. That's defined as the number of hours elapsed since your plane left the ground. Could x be 4? Sure, right? X could take on the value 4. Could it take on the value 10? Yeah, could it take on the value negative 0.5? Yes. Half an hour before your flight took off, right? So it's like 30 minutes before. All right, so that's more that we want to think of this x as, you know, it has a real world meaning, and it varies, right? Maybe we think of it starting from negative 1, and then taking on every value, negative half, 0, 0.1, 0.8, 1, 2, 4, 4.5. It's taking on all those values as time goes by, okay? It's just that for this equation, so only 3.5, maybe that's when you got your peanuts, right? So that in the plane, or you paid for your peanuts, right? Now you have to pay like $5 for a bag of peanuts, right? Okay, so maybe the 2x minus 7 has to do with some particular point at time in your flight. But x takes on all those values of time since you left the ground. Make sense? Variables vary, right? Variables vary. Okay? So x could take on, in fact, x could take on any real number. All right? So then we have another variable called dx. Dx, that should be slightly familiar from Calc 1, hopefully. And so what does that represent? So a variation or a change. So technically, this is a variation. It's like how x varied from one value to another. And then how much did it vary, right? So that's what we mean by a change in the number of hours elapsed. How much did x vary from one value to another? So maybe like, oops. So maybe, x was 2.5 hours since we took off, and then x was 2.9. So we're talking about the variation of x from 2.5 hours to 2.9 hours. X took on all those values in between. So in that situation, what would dx be? 0.4, right? A variation in time, how much time passed, a duration of time, right? So dx, the thing that's a little bit different about dx is it can start at any x value. So I could say x equals 10, x equals 13.1. Long flight, right? Where are we going? Madagascar. Okay, so dx equals 3.1. So that's the thing that's a little bit different about dx, is that starting value of x is, it can start at any value of x. Okay, so in this case, dx is 3.1. Again, a variation, when we see dx or dy, we're thinking about a variation in that variable. Okay? And as a short terminology, we'll also say a change in the number of hours. But what we think is it's how the variable varied from one value to another. Okay, so that's principle 0. So we always, as we're working through this stuff, it's always about how variables are varying quantities. Okay, principle number 1, rate of change. So let's do an example here. You're buying some trail mix. It costs $3.20 a pound. So you put some in your bag, but then you say, no, I remember how really good this trail mix is. I want more. So the question is, what additional cost will you pay for 1.5 more pounds of trail mix? So I'm going to scoop out 1.5 pounds more. And so I want everyone to figure that out on your own. It should be an easy question. So just figure out, how would you figure out how much more you would pay if you put 1.5 more pounds of trail mix in your bag? Go. Everyone just figure it out on your own. Do the math. Write it down. And we're going to come back to that question in a sec. Okay? So I just... Okay. Okay, so whenever we're working in this class, we want to get out of the mentality of what are the numbers, what are the formulas, get my answer. All right? So it's going to be different than that around here. Okay? It's not going to be, okay, get the numbers, what formula do I use, get the answer. It's always going to be about, how do I understand what's going on first? I want to understand the situation. Okay? And then, once I understand it, then I want to model it with mathematics. So that's what we're going to do here. We want to define these variables. I got 5 variables here: x, y, dx, dy, and m. And I want to take the information given and I want to model it with these variables. Okay, so I'll give you the first one. So what I'm looking for is phrases, written phrases that describe completely and precisely what we got. So I'm going to tell you that x is the total number of pounds of mix in your bag. Okay, that's the total number of pounds of mix in your bag. So from that, and given the context, you're going to write out what is y, what is dx, what is dy, and what is m. What is m, okay? So you're going to write those out, and then meet the person next to you, and see, you can work together, or you can work apart, and then compare how you did with each other. Okay, so you're free to talk, or work by yourself at first, but eventually everyone's talking to the person next to you and seeing how you did. Go. All right, so y. What'd you say for y? Was that?
The total cost of the mix.
Total cost of x pounds, right? Total cost of x pounds in dollars. So we want to be precise and use units. Total cost of x pounds in units. So then what's dx? Okay, a variation in the number of pounds. Okay, so, or you could say a change in the number of pounds, right? So it's how much x varied in pounds. Dy?
Change in the cost.
Change in the cost. And then m?
Cost per pound.
Cost per pound, or the rate of change, right? So this is the constant rate of change, $3.20 per pound. Okay, so going back to the original question, what additional cost do we pay for 1.5 more pounds of trail mix? How much did you calculate for that?
480.
480?
Plus the, yeah, you're adding 1.5 total would be 70.
What additional cost will you pay
Oh.
for 1.5 more pounds? How much?
3.8.
I'm going to put 1.5 more pounds in a trail mix. I'm asking what additional cost will you pay for that? $4.80? And you got that by? Yeah, you took the 320 and you multiplied by the 1.5, right? And that got you the additional cost for the additional 1.5 pounds. So what I want you to do is, I want you to write an expression using these variables that recreates what you did when I asked you that question. When you did the math, it was easy. So now I want you to recreate that solution using one or more of those variables. You might not use them all, but using x, y, dx, dy, and m, how could you symbolize that calculation you did to get that answer? Everyone think about it? The first question is, what was it asking you to solve for? What was that question asking you to solve for? I heard y. Is it asking you to solve for y? Not y. dy, right? It was asking you to solve for how much variation in your, how much did your cost vary, right? How much more did you have to pay? That's variation, right? And what is dy equal? M dx. Okay? What does this tell us? This tells us that for any variation, for any variation in pounds, we know immediately what the variation in cost would be, right? If I tell you that we're going to put 10 more pounds of trail mix in the bag, you know instantly how much more you're going to pay. How much more are you going to pay? If I put 10 more pounds in, dx, my cost is going to go up how much? $32, right? $32, because it's the constant rate times the change. This is the principle we're going to use to, this is how we understand this number, 320. The constant rate of change. Given any change in the number of pounds, that 320 tells us how much the cost will go up. You just multiply, and how does it? You multiply the 320 times your change in pounds. And you get the change in cost. Okay? It may take half or 3/4 of the semester for us to finally get that. Sounds simple, but I'll ask it many times. And you all look at me like, what is he talking about? I'm talking about that. This is like the bedrock of this idea of, you know how fast the quantity is changing every moment? You want to know how much of it you have. Where do we see how much it's changing? This right here. That's how the quantity of cost is changing. And then this is kind of like how much we have. dy. It's kind of like how much more we have. Right? You know how much something is changing at every moment? In this case, moments being pounds. M. You want to know how much that you have. So dy is in terms of this is how fast cost is changing, right? This is how fast the cost is changing per pound. This tells us how much cost we have, right? How much it's going up. So this is like the very core of this endeavor. You know how fast the quantity is changing. You want to know how much of it you have. Okay, questions on this slide? Anybody have a question? All right, so now we're going to remove 0.4 pounds from the bag and return it to the bin. When no one's looking, right? When no one's looking. Okay? So go. So what would dx be? What would dy be? And what would m be? So dx, they retain the same meanings, but what would their values be? What would the value of dx be? In this situation, dx is 0.04? Negative, right? Variations can be negative. Decrease, right? Decrease. Okay? So then what's dy? Given any change in pounds, we can know the change in cost by doing m dx. What is that? Negative
1.28.
28? How can cost be negative? How can cost be negative? It's a decrease, right? So it's telling us that our total cost went down. M is still the same thing. It's the constant rate. Is it negative 3.2 now?
No.
It's still positive, right? Make sense? Make sense? Any questions? All right, new scenario. A soldier loads an American flag from the top of the pole at 0.75 meters per second. The question is, how much does the height change from 0.6 seconds to 2.4 seconds since the flag left the top of the pole? So we're going to start by understanding and modeling the situation, right? We're not going for answers right away. We're going to start by taking the information and modeling it with mathematical symbols, right? Take the information, the real world situation, and model it. So I'm going to tell you that, I told you this time, I tell you y is defined as the height of the flag in meters. Okay, so that one's given. So this time, you're not only going to write out the English words, the sentences, the phrases, but then you're also going to determine, is each one of those, in this particular situation, is the value of each one of those known or not? And if it's known, what is it? Okay? So I'm going to return to attendance. But again, so you're going to, again, define x precisely and thoroughly, and then say, do I know the value of x given this in this particular scenario? X varies, but we can kind of look at a certain situation and say what are its current values, right? So for each one, define in words, and then if it's known or not, and if it's known, what's the value? Ready, go. What'd you say x was, Victoria? What's that? Total number of seconds. What do you think? So whenever you do a time variable, you always want to have that reference of since when. So when would it be? So number of seconds since started to be lowered, right? So yeah, good. So we want the number of seconds since the flag left the top, or since lowered, right? Because we could define different time variables here, right? So we don't. So definitely we don't want to say just time, even time in seconds, right? So since when, right? Since when? Okay, and we know the height of the flag. So then what would dx be? Change in time in seconds, and we think of that as a variation in time, right? Time varied through some segment of time from a start to a finish, right? dy.
Change in height.
Change in the flag's height.
Meters.
In meters. Change in the flag's height. And then m is?
0.75 meters per second.
So, what's that?
The rate of
The rate at which the flag moves, right? The constant rate of change, and its value is?
0.75.
0.75, right? Okay, how did we define y? Y is the height above the ground. Which way is positive y? Up. Which way is the flag moving?
Down.
Constant rate of change is?
Negative.
Negative 0.75. So the rate of change depends on how the y, the thing that's changing, is defined. In this case, height is defined positive upward. If it's moving down, then that rate of change is negative, right? Okay, so x, is it known or not? What's that? Yeah, we have a starting x and a finishing x, and so it's kind of known. It's like x starts at, so we can say like x initial is 0.6 seconds, and then x final is 2.4 seconds, but variables vary. So what is x? What's that? So The height from 0.6 seconds to 2.4 seconds since the flag left the top of the pole. So that's saying that we're looking at a duration of time starting at 0.6 and ending at x equals 2.4. Does that make sense?
That will do the change when it's like saying X starts when the flag starts at the top.
Yeah. Yeah, so you could think of any value of x as a change since 0. Does that make sense? Yeah, so it kind of, yeah, so 0.6 seconds is like we're pausing time at 0.6 seconds, and yeah, that is the same as the change since 0. But it's a value of x. So x initial is 0.6, x final is 2.4. What is x?
Haven't we defined it already?
Every value from 0.6 to 2.4, it varies through those values. X is 0.6, then it's 0.65, then it's 0.7, then it's 0.8, then it's 0.92, then, right? X takes on, it's a variable. It takes on every value from that to that. So we have an initial x, a final x, and in this scenario, x takes on every value in between. Variables vary, okay? All right, what about y? Is it known? Why don't you know it?
It's not the initial height.
You don't know where the initial height is. You don't know how high it was to start with. So this is unknown in this duration of time from 0.6 to 2.4 seconds. All right, what about dx? Is it known?
Yes.
The variation in time is 1.8 seconds, right? Or final minus initial, right? Final time minus initial time gives us the variation in time. Okay, what about dy? Known? We can figure it out, right? So it's not given, but we can figure it out. How do we find the change in height? Equals? This tells us for any change in time, we can know any change in height, right? That's what the negative 0.75 tells us. We can pick any change in time we want and can calculate the change in height by doing
Negative
0.75 times
dx.
times the dx. dy equals mdx, right? So this formula is what this number means. This formula is what this number means. It means given any change in time, we can figure out the change in height by multiplying it by that number. Multiplying the change in time by the constant rate of change gives us the change in height. And what is that? 3.5? Units? Meters. A decrease, so this dy is a decrease in 1.35 meters. Any questions on modeling and doing the math on that problem? Doing good. Okay, so now I want, instead of saying there was an initial time and a final time, I just want to have an initial time, 0.6, and then I'm just going to imagine x takes on all the values starting from 0.6. Okay, but it's still the time since we started lowering the flag. Okay, so I'm going to start from x is 0.6, and then I'm going to let x increase from there, right? 0.7, 0.8, 0.9, 1, 1.1, etc. Okay, and we do the same thing again. So now x is truly variable, taking on all values, but we're going to think about from the starting point of 0.6 seconds. Okay, so what is? So if we have dy equals mdx, then how much does the height change from 0.6 seconds to x seconds since the flag left the top of the pole? So let's go back here. How would you say, how much does the height change from 0.6 seconds to x seconds? What would it be?
Wouldn't it just be x minus 0.6?
Yeah, so x minus 0.6 times negative 0.75 meters.
So I got two possible answers. So that x minus 0.6 and x minus 0.6 times negative 0.75
meters.
What was the
first one is. We want to know how much the height of the flag changes or varies. And what variable was that? That was our dy, right?
Yeah.
And this is referring to our, which equals x minus 0.6. So we can still use the same principle to calculate dy, given any change in time. Now our change in time just has a variable in it. That doesn't bother us, okay? Because it could take on many values, right? And then x minus 0.6 takes on many values. But we can still write what dy is. What will dy be? Negative 0.75 times dx, or x minus 0.6. So dy is the change in height. M is the constant rate. Dx is the change in the number of seconds. And so we get, so what we get is, this question that we're asking is really, we're asking about a function. We're asking what is the net accumulation function for the flag's height? What do we mean by function? X can take on many values, and then you get many values for change in height in return. That's what we mean by function. And we said that was? So that's an H, and you can't read that very well. This is the wrong PowerPoint. It's close enough, but it's the wrong one. Okay, so this is what this is supposed to say. This. So capital A for accumulation. In this case, accumulation of changes in height, right? Accumulation of changes in height. So we've got the subscript H, which we were calling y, okay? So that's kind of like what we said before was y. Now I'm saying H. So this is like accumulation and changes of H given some x. And what is that? That's going to be negative. Well, that's our m dx. So when you let x vary and you ask this question about how much does the height vary, you're really asking for a function. You're asking for a function. Given any value of x, what's the... So if x was 1.6 seconds, this function would tell us then what's the change in height, or the variation in height. At 1.6 seconds, how much variation in height would we have since 0.6 seconds? Negative 0.75 meters, right? In that 1 second from 0.6 to 1.6, the flag's height would decrease 0.75 meters, but then this function tells us how much it would decrease for any value of x. Does it make sense? So this is principle 2. Principle 2 is net accumulation function. So principle 1, rate of change. What gives us the meaning? So if the rate of change is m, what gives us the meaning for that? If I have a rate of change of m, what gives me the meaning for the value m? How do I get my meaning from m? Nope. Well, that's how you calculate it. But my meaning comes from dy equals m dx, given any change in the independent variable. M times that change in the independent variable gives me the change in the dependent variable. Okay, so that's principle 1, rate of change. Principle 2 is net accumulation function. Okay, so here's that same scenario. So what I want you to do is, I want you to sketch the rate of change function make some axes like these on the left. Sketch the rate of change function. So this, what are our axes here? This axis is the x-axis, and it's the same meaning as our x. Time in seconds since the flag left the top. Over here is rate of change, right? So what are the units on this axis here? Units. Meters per second, right? And then over here, I want you to sketch the net accumulation function. But I want you to scrap the formula that we found. Just put it out of your mind. I want you to sketch this net accumulation function thinking about the situation, not taking that function that we wrote and so pretend you didn't have it and you're just thinking about the situation, okay? So I'm not asking you to plot points or use slope and intercept and these kinds of things. What I'm asking you to do is to sketch this function given the situation. What will that function look like, okay? So net accumulation function. What you have on the y-axis is going to be changes in height, and what will the unit be for that? Or variations in height? units will be? It's meters, right? Meters. So on the left graph, so I should put units here. X is seconds. So we have seconds since the flag left the top of the pole, and then meters per second on this axis, and meters, in fact, the change in meters on this axis. And you're going to, as I keep doing attendance, you're going to sketch both of these graphs and then talk, all right? And get help if you need help. 0.75 for every time, right? Oh, I already... I had it all pretty for you, and I still wrote it. Okay? Number of seconds, rate of change of height, net change in height. There's the rate of change function, right? And as time went by, so looking at that graph right there, what does it consist of? What is that graph made up of? Points. As time went by, points were generated. This time and this rate of change. This time and this rate of change. Each point is a correspondence of a time and a rate of change. It's just that the rate of change is always negative 0.75. So you end up with a horizontal line of points. You look at that line, you say, that's a bunch of points. Okay? For that second one, here's a hint. Ask, what is dy at 0.6 seconds? That might get you on the right track. What is dy at 0.6 seconds? That might get you on the right track. Now over here, I asked this question, what is dy at 0.6 seconds? What is it? But remember, it was negative 0.75 times. We wanted the net change since 0.6 seconds. So at 0.6 seconds, how much change have we seen in the height? 0. So doesn't that make this a point on the graph right here?
Yep.
And then as time progresses from there, what are our net variations in height? More and more negative. So what will this look like? Did anybody get this? Anybody get that before I put it up there? Okay. Those who didn't, doesn't make sense. So this is not the height function. This is not the height of the flag. It's changes in the height since that starting time of 0.6 seconds. So as time goes by, you see more and more of a decrease in height. Doesn't make sense now that I put it up there. Please, question?
Doesn't that make the net change greater each time?
Greater negative, right? Because those dy's are negative. So it's a greater and greater negative value. Because because our rate of change is negative and the changes are all negative, but greater and greater negative. So yes, greater that way. Other questions? Happy weekend.